I would like to show you two examples of factoring in Boolean algebra. This specific example we've seen before. It's x plus x times y. Again, we agreed on the order of operation. The multiplication comes first. When we have addition, multiplication, there's no parentheses indicating which one we should do first, and then we use the multiplication. So it's the same order of operation as we use in arithmetic. Now, we can factor x out in the same way as we do in algebra, in our normal real number algebra. And the reason we can do that is because x can also be written as x times 1, right? X times 1 is the same as x. Remember, we're in Boolean algebra. This has nothing to do with the arithmetic. The reason that x times 1 is x is because it doesn't matter what x is. If x is 0, then when you do and 1, 0 and 1 is 0, so you get x back. If x is 1, then you do 1 and 1, you get 1, so you get x back. That's why x times 1 is x, okay? So let me put that in here. Y, if x is 0, x times 1 is 0 times 1. This becomes 0. 0 equals 0. Good. If x equals 1, then you have x times 1 equals x. You want to check that. Then 1 times 1 is equal to 1. Yes. Okay. So it's really easy to prove a formula in Boolean algebra because all you have to do is to plug numbers, and we only have 2 values for each variable. So it's pretty easy to prove. We can never do that in regular algebra because we would have infinite number of values of x, so we couldn't test, for x equals 1, x equals 1.1. It's infinite. We couldn't prove that. But in Boolean algebra we can. We can simply exhaust all the possibilities. So x times 1 is x. So that means I can write this x here as x times 1, right? And now this is the reverse of the distributive property that we saw before. Okay. Finally, 1 plus y is always 1. Any Boolean expression, it can be small or large. When you add 1, the entire thing becomes 1. Okay? So that's because no matter what the expression is, if it's 0 plus 1 is 1. If it's 1 plus 1 is 1. So this is 1, and x times 1 is x. X plus xy is equal to x. Now let me, before I go to the next example of factoring, let me draw the diagram for this. The diagram here, the diagram of x plus xy is what? Well, here we have x, here we have y, and we're doing multiplication first, okay? So we do x times y first. And then with the result of that, we add x. That means to put x over here and then combine with the OR gate. This becomes x plus xy. Okay, so that's the diagram for x plus y. So this simplification here, this factorization, it really means that this entire expression is simply x. Okay, so that entire logical gate, let me move this over here. This entire logical gate is simply x, so that entire thing can be replaced by just x. No gates whatsoever. Okay, so these two diagrams are the same, and we can test that, right? So if we make a little truth table here, here is x, here's y, so it's 0, 0, 0, 1, 1, 0, 1, 1. Let's see what x is, and let's see what x plus xy is. Okay, so that's the expression diagram of x plus xy, and here's the diagram of x. If x is 0 and y is 0, that means x is simply 0. It doesn't matter what y is. And then here, x is 0, y is 0, so the entire thing is 0. If x is 0, y is 1, this is still 0, and this will become 0 plus 0 times 1. So 0 times 1 is 0, 0 plus 0 is 0. X is 1, y is 1, so this becomes 1, and that will be 1 plus 1 times 0. 1 times 0 is 0, but plus 1 becomes 1. And then if both are 1, x is 1, and then here is 1, this is 1, this is 1, the entire thing is 1. Now you can see that both are the same outputs. This means that x is the same as x plus xy. Okay, that's another way you can prove that the two formulas are the same. So we did that algebraically here, right? We factor and we show that that's the same as x. Or we can do that by simply exhausting all possible values of x and y. So this is telling us that y here doesn't make any influence. Y can be anything, it doesn't matter. Both expressions will be the same. It will really be dependent on x. Okay, now let's take a look at the other example that I would like to show. This one is an unusual, very unusual factorization that is not found in the regular arithmetic or algebra that we know from calculus and algebra courses. And this one is this, x times x plus y. Okay, now this is unusual because here we are factoring an addition out. So here we're factoring the multiplication out. See the multiplication, x times 1, x times y, and then the multiplication goes out right here. And then what's left inside the parentheses is the addition. So that's very intuitive. We already know how to do that in regular arithmetic. But here is very unusual because we can also do a similar thing with the addition. And this is how we do it. Well, x, I can write x as x plus 0. Okay? So x plus 0. Now notice that I can factor x plus out. That's the second distributive property from the Boolean algebra. So this is the same as x plus, and then inside the parentheses we put 0, and then times the y here. Okay? So let's go back here. Here we're factoring the multiplication out. See, here's multiplication. We put it out of the parentheses. Here we factor the addition. Here's addition. We put it out of the parentheses here. What's left is the 0 and the y. Okay, now x plus 0 times y, that's 0. X plus 0 is simply x. So it turns out that this expression is the same as this one. Well, if you take a look at this carefully, you will see this is the same as the first one that we work with. This is x times x, right, plus x times y, if we distribute that. And y'all remember what this is? X times x, that's simply x. So that's our old expression. That's the first expression here, x plus x, y. So I just wanted to show you another way of factoring, which is very unusual, but it can be done. Okay.